Minutes of sunshine in the schedule, so they cut a little bit the presentation. Okay, so maybe we can start. I want to tell that I met Nicola Rizzi more than 25 years ago, and even if we never managed to write a paper together, we have a strong scientific interaction. I think this talk will be related to the first one of Angela, but also somehow to that one of Stelios.
Okay, thank you very much. What Francesco has just said is that I am an old man. So anyway, in this talk I want to present and discuss a procedure in order to derive a 1D model for a plate-like body that is starting from the Koiter shell theory. And this presentation is at least twofold, because I want at first present the procedure in order to derive this model for a single plate, and then discuss the possibility to make a model also for an assembly of plates. So let us start with the plate-like body in its reference configuration. Then you can consider its middle plane and a Cartesian coordinate system as shown in this picture. Then, if I consider the plate middle surface, at each point of the coordinate system I can attach an orthogonal basis shown here, and the first assumption that follows the assumption made by Koiter is that the plate obey the Kirchhoff-Love assumption, that is, the E3 vector remains during the motion orthogonal to the span of E1 and E2. If one consider also the so-called Vlasov assumption, one has to take into account also this constraint, that is, the vectors E1 and E2 remain orthogonal. I want to stress that the first assumption is compulsory because it's the assumption made by Koiter. The second one can be removed, even though in my presentation I will consider both the assumption. In this way, the plate motion, in view of the first assumption, is completely described by the motion of its middle surface. Because if you consider that the vector E3 is orthogonal, the motion of the plate-like body is completely described by the motion of its middle surface. And if you consider also the second assumption, this means that at least on the middle line, that is the x-axis, the basis E1, E2, and E3 is made by vectors which remain orthogonal. Now, the second assumption made in this presentation is that the displacement approximation of the plate middle surface, which is a function of the two coordinates x and y, can be described by means of a linear combination of functions which are of the sole x or the sole y. And in particular, I will consider the case in which the functions of the y variable may be assigned. So, if we consider a generic, a present configuration of the plate middle surface, we can describe at each point the tangent vectors or to the coordinate lines by making the derivatives or with respect to y and x of the transplacement function, and then it's easy to compute the vector which is the normal unitary vector to the surface. So following the Koiter assumption, we can easily calculate the metric tensor of the surface and the curvature tensor using both the tangent vectors and the unitary normal vector. Then the plate deformation measures are the metric tensor minus the identity tensor and the curvature tensor itself. Note that if I implement the Vlasov assumption, that is the Vlasov constraint, I have to require that this component of the metric tensor should be 0. I want also to stress that in this way, as f is function of x and y, of the sole x and y coordinates, the deformation, the components of the deformation tensors are functions of xy as well. Now, I can consider the elastic energy of the plate in the form given by Koiter and Simmons and rewritten by Sierle recently. And in this form, you can see that dividing the energy elastic density in two parts. The first one giving account of in-plane deformation, and the other one giving account of the flexural deformation, you can see that there are the deformation tensors, of course, and also the h, the parameter h, which is the height of the plate-like body, that is the thickness. Of course, I have to remind that in the Koiter assumption, the thickness should be small, relatively small, with respect to the other length of the plate. Now, if you consider the present shape of the x-axis, which is red, depicted red in this picture, so you can define in the by making the derivatives of the shape function with respect to x, you can define the tangent vector, the normal vector, and the binormal vector, that is the Frenet frame at each point of the present configuration of the curve. Then, following Love, we can introduce the torsion angle, which gives the possibility to describe the present configuration of the base vectors, the base vectors given in the reference shape, to the actual point, that is the Love's twist angle gives us the possibility to rotate the Frenet frame in order to obtain the present shape of the base vectors. Then, using the derivatives of the Frenet vectors, we can obtain a description of the classical curvature, torsion, and extension of the beam. So we can define 4 deformation measures which are associated to the one-dimensional curve, that is the elongation, the 2 bendings, and the torsion, where the definition is given in terms of the displacement vector and the rotation vector and the Lave's angle. So it can be shown that in this case the plate deformation measures I have introduced before following Koiter can be rewritten in terms of the beam deformation measures, that is, in terms of these measures introduced before. So the energy density of the plate can be rewritten in terms of the deformation measures of the curve I have introduced before. So you can see this is the expression in which, look, in the yellow circles or ellipses are terms related by the y coordinate, and the other terms appearing here are given in terms of the extension, curvatures, and torsion. So you can see that the energy density in this form is highly nonlinear in the beam deformation measures. So we can give a power expansion of this energy and integrate the expansion itself along the y direction, so arriving at a form like this one. Here I show the expression of the energy up to the second order expansion on the beam deformation measures, and taking the derivative of pi of the energy, elastic energy density with respect to the components of the deformation measures, we obtain the classical beam stress measures, that is normal force and bending moments and twisting moment. Okay, just to stress that the first order terms are the classical Saint-Venant terms, but the main point is that in this way you can obtain constitutive relationships which are nonlinear in the deformation measures. Now, I want to show just a few results. At first, I consider a thin strip that undergoes a very severe torsion. That is, you can see on the slide that I have considered a case in which the rotation, the strip is built in at one end, and free, completely free at the other end. And in this case, we have considered a rotation of the end section of about an angle which is quite is pi, is very, very high. So in this graph you can see the solution of this problem, in which in this graph is reported the relationship between the torsional curvature and the extension. The solid line, the solid curve, is the reports results obtained by using the model I have introduced in the presentation, and the other curve, this continuous curve, gives account of the results obtained by making 3D plate elements by using the finite element code abacus. What one can see in looking at this picture is that apart the fact that the results obtained seems to be in very good agreement, it is shown that such a continuum model shows relationships between the extension and the torsional curvature of the beam, of the continuum. This is an effect that can be called pointing effect, relating to the experiment of pointing at the beginning of the 20th century, and it is a typical phenomenon in other fields, for instance, when one deals with soft materials. But in fact, it is shown also in this case. Then I will consider also a case in which, I'm sorry for the picture, which is not very fine. Anyway, I will consider the strip analyzed before with other two smaller strips attached at the upper side and lower side. And we have considered three more cases in which the strip remains the same and the length of the upper and lower strip is increasing. The same plot shown before is reported here, and one can see that in the case of small value of the width of the lateral strips, the results obtained by the one-dimensional theory and the and abacus are in good agreement, but when the strips become larger, then the results are no more in agreement, and we think that this is an effect of the in-plane deformation of the cross-section that is not taken into account in this model, but of course that can be inserted in a more refined model. So I come to the conclusions, and I want to stress that starting for a three-dimensional plate-like body, exploiting the Koiter theory, a one-dimensional model has been derived. This is the procedure gives a plate displacement by approximating the assigning the deformation along the y-axis. That is, as I have shown, the displacement function is given as a linear combination of functions of the sole x or y-axis. Then, integrating along the y-axis, one comes to the one-dimensional model. And due to the fact that I have used the Frenet frame and the constraint, the 1D model results to be a higher graded continuum, because you can remember that in the Fredé theory, the torsion depends on the third derivative of the yes. The third derivative along the axis of the twisting angle. Okay. A plate assembly can be constructed by joining the plates, and some comparisons have been shown with the abacus solution. Okay. Thank you.
The small plate strips will bundle. Is this included in this analysis?
Yes, as you have a nonlinear model, that is, the kinematical quantities are given as a nonlinear functions of the displacement angle, and you have also nonlinear constitutive relationships. You can also recover buckling and other phenomena related with instability. Yes.
Of course, warping, the degree of warping and the overall here, the gap between twist and bending is of course driven by the stack.
Yes.
So, of course, I don't think this is explicitly included in your formulation. Maybe, probably, I mean, to what degree can we incorporate this effect later on in the refined model?
Okay. In the case I've shown, I consider the Koiter theory, and the Koiter assumptions are that 1, the thickness is small, 2, the Kirchhoff-Love hypothesis is respected, and 3, the material is is hyperelastic. So this is for one strip, but if you have, for instance, a composite or a laminated plate, I think you can consider, if it's the case, that each one of the plate is hyperelastic, but with different materials, and so you can make a combination. Okay?
So you think it as a building block?
Yes, in a sense.